Welcome to Review 2B, which is just a review of the salient parts of Reading Assignment 5. So this is the last review lecture and the last slide for this course. I've just summarized the contents of the slides to follow here, so we will just move forward. Again, I'm only summarizing key points, conventions, procedures, and again I'm going to basically only highlight certain things since we've discussed this material in greater depth in the previous lectures. All right, so one of the things we realize first of all that any vector field can be decomposed into two types of field, a source-free field and a rotational field. And also we found that under specific conditions where symmetry applies, and it would be very simple to apply the divergence theorem in the case of a rotational problem and Stokes' theorem in the case of a source-free problem to solve for the vector field. Also, we can use a principle of superposition if we have multiple objects where each of the objects exhibit a form of symmetry. So just briefly, Helmholtz equation essentially said that we can represent a vector field in terms of the gradient of a scalar potential, and this was actually the flux component of the vector field, and the curl of a vector potential, and this was the circulation component of the field. And these are unique for a given physical vector field under specific conditions, and you refer to the note here that the solution to F is unique if the rho, which is scalar density, and J is a vector, decay sufficiently fast as you approach infinity. And this is the case in practice. All physical problems generally will obey this condition. All right, so we basically were able to take this equation, take its curl, and if you take its curl, you get this result, and also making use of one of the vector identities before, that the curl of a gradient is 0, meant that the curl of the field could be simplified down to just the curl of a vector potential A, and we call this whole vector here J. If we take the divergence of the vector field, then we end up with minus divergence of the gradient phi plus the divergence of the curl of A, but from one of the vector identities in the previous lecture, we can say that the divergence of the curl of a vector field is always equal to 0, and therefore this simplifies down to a scalar function which we called rho. And typically what will happen is rho is given and J is given, and in principle you can solve for the vector field F. But we were dealing with two different types of problems where symmetry can be applied. One of them basically is in a rotational field, in which case the curl of the field will be equal to 0, and the divergence F is a given, or you can have a source-free field, in which case the divergence of the field equals 0, and the curl of the vector field is equal to J. So in this case, we can apply the divergence theorem to link rho to F. In this case, we can use Stokes' theorem to relate J to F. And the types of symmetries where it was possible to apply the divergence theorem and Stokes' theorem in the respective problems was when we had planar symmetry, cylindrical or spherical symmetry, when we were dealing with any rotational field. In that case, as I said, you use the divergence theorem to solve for F. In the other case, which is a source-free problem, if J has planar symmetry, solenoidal symmetry, which is basically a circumferential current flow, cylindrical symmetry, which means an axial current flow, or toroidal symmetry, then we can use Stokes' theorem to solve for F. And the principal superposition in a nutshell is shown below. If we have a symmetry problem where we know we can solve for F1 given a J1, and we have a second problem involving a current flux density J2, and again because of symmetry we can solve for F2. Then if we take the sum of the two vector fields, that is F equals F1 plus F2, and then basically take the divergence of the total, and then basically because of linearity we can say that the divergence of F is equal to the divergence of F1 plus the divergence of F2, and so the sum of these two would be equal to rho. And so this rho, which is for the total problem, could be broken up into its constituent parts, representing two different problems, or as we call them, subproblems. In this case, basically here, curl, you'd have a J1 for this one and a J2 for this one. If you basically take the curl of the total vector field, again because of linearity, this can be curl of F1 plus curl of F2, which is J1 plus J2. So given a J, You can break it out into two independent j's, each having a specific symmetry. Solve for each one of them, sum the results, and get j. Okay, so effectively, these are the problems that we were dealing with. Now, typically what will happen is you either have a problem where rho is non-zero or j is non-zero. Those are the only cases where we really can consider where symmetry applies. And so that's why we're dealing with these sub-problems up here. All right, what are the classes and problems in the procedure for superposition? So, problem consisting of multiple objects is converted into a number of sub-problems reflecting the number of distinct objects. So, for instance, if you had a sphere and a cylinder, then basically a sphere would be one problem and cylinder would be a second problem. Each sub-problem exhibits a specific type of symmetry, and calculations for each sub-problem are performed in translated coordinates. In other words, you are not guaranteed that the cylinder happens to be lined up with the axis of symmetry. So what you do is you presume that it's lined up with symmetry, axis symmetry, and then afterwards you move it back to its original location. Once you basically have done that, then you sum the results, basically get the total vector field. So that's more or less what's basically indicated here. So we have basically point of symmetry if we're dealing with a sphere, plane of symmetry if we're dealing with a slab, and we have axis symmetry if we're dealing with anything which has a cylindrical symmetry. So the two classes of problems are as follows. Objects that appear to have no apparent symmetry can be separated into two or more objects where symmetry applies to each individual object. And then the final result is the superposition of the vector fields for each object. So that's one possibility. The other possibility is objects with different geometries, each having a given symmetry, can be treated as individual problems and solved. In other words, they're distinct problem geometries from each other. And so it's clear just by visual inspection that you have, say, a sphere and a cylinder. Again, the final result is the superposition of the field vectors for each object. So what is the superposition procedure in a nutshell? Well, the sequence of steps to compute the total field at a particular point is as follows. The first step is to determine the field for each source in an appropriate coordinate system. The second step is to convert the field for the source in each subproblem into Cartesian coordinates. The third step is to rewrite the fields for the individual subproblems with respect to the observation point. And the fourth step is to compute the total field. All right, so we can now summarize how we went about computing fields for problems where the field is irrotational, has a high degree of symmetry, and to determine if superposition is required. And so under these circumstances, where the field is rotational, we had the following two vector equations. The curl of f equals 0, and the divergence of f would be equal to rho. And we were able to apply the divergence theorem, and the left-hand side was just a closed contour integral, a closed surface integral, which we call this surface the Gaussian surface. And on the right-hand side, we end up basically with the total charge enclosed by this closed surface. Well, the calculation procedure for computing f was, first of all, determine the nature of the symmetry and determine if superposition is required, which meant more or less the creation of subproblems for a given problem. Second was to establish the mathematical form of the field and establish the shape of the Gaussian surface that satisfied one or more of the following criteria. The surface could be one continuous smooth surface, or it could be a number of disjoint surfaces stitched together. The vector field f is parallel to ds, and f dot ds is a constant on any of the discrete surfaces. That's one possibility. Or the vector field f is orthogonal to the surface area vector on any of the discrete surfaces. Third, compute the left-hand side of the divergence theorem. The left-hand side needs to be computed only once. Fourth, compute the right-hand side of the divergence theorem. And finally, equate the left-hand side with the right-hand side and compute f. All right, so then the geometries we considered which had a high degree of symmetry included planar, cylindrical, and spherical. And for the left-hand side of the divergence theorem, we could look at a number of cases. For example, slabs parallel to the x, y, z, y, or xz planes, and the Gaussian surface in this case is a six-sided rectangular box. And typically what you'd find is that you'd end up requiring two surfaces, field on either side, assuming that the Gaussian surface is included the whole slab. But because of symmetry, it turns out that f of x2, that is the field on one side, or the flux on one side and the flux on the other side, were essentially the same. And so we only have one value that needs to be computed. This is just for the other two conditions, in this case basically xz plane and xy plane. For a cylindrical case, on the left-hand side, we ended up with this being equal to 2 pi times the radius of the Gaussian surface times its height. And f of r, of course, is the scalar that we're trying to determine, and it is a function of r. And for a spherical, basically, we ended up with 4 pi r squared, f of r being the radius of the Gaussian surface. And again, f of r is a scalar function to be determined. Just again, a reminder that for planar geometry, there are two surfaces which provide a non-zero contribution to the flux, and this is more or less what was described here. And second is that the vector normal to the Gaussian surface is in the same direction as the field. All right, so then we looked at the case where the field is source free and we wanted to compute the field of the problem. And of course, we assumed high degree of symmetry, and then also need to determine if superposition was required. So the vector field equations under these circumstances would be the ones shown here. The curl of F is equal to a current flux density if we're dealing with problems involving electromagnetics, and the divergence of the field would be equal to 0. Under these circumstances, we could apply Stokes' theorem. The left-hand side involved a closed contour integral, and the right-hand side basically was computing the total current enclosed by the contour. And here, again, we need to concern ourselves with convention, that the right hand is in the right fingers are in the direction of the contour traversal, and the thumb points in the direction of the area vector. All right, calculation procedure to compute f of the field was as follows. First of all, determine the nature of the symmetry and determine if superposition is required, which meant the creation of subproblems. Secondly, was to establish the form of f and the shape of the closed contour that satisfies one or more of the following criteria. One, that the vector field f is parallel to the tangent to the contour on a given segment, and f is constant at each point on the same contour segments. Hence, the dot product between the field and the tangent vector, differential tangent vector, is either the magnitude f ds or minus magnitude f for ds. And as a result, f can come outside the integral. Or we could have that the vector field f equals 0 on a contour segment, hence f dot ds equals 0. Or thirdly, the vector field f is perpendicular to a tangent vector on a contour segment, hence the dot product is equal to 0. Third step was to compute the left-hand side of Stokes' theorem. And again, it only needs to be computed once for a given geometry that has a specific form. Fourth was to compute the right-hand side of Stokes' theorem. And finally, to equate the left-hand side with the right-hand side, and then compute the field f. All right, this is then in summary form the different geometries we considered. We looked at planar geometries, toroidal, solenoidal, and cylindrical. And again, the planar case and the solenoidal case shown here, there are two contributions on the left-hand side of Stokes' theorem. So for the case of a plane, we'd have basically a contour segment which resides on one side of the slab and a contour segment that resides on the other side of the slide. So if we compute the circulation component on one side and the circulation component on the other side, we find out that the two values, Fy1 and Fy2, are exactly the same because of symmetry. And so as a result, we're only having to solve for one because it's implied that the two are equal to each other. This is a case where the field is basically parallel to the x-hat direction, and this is that the current flux density is in the z-hat direction. Here's another example where the slab orientation is different, and there's a third case. This is not exhaustive in the sense there are other situations one could consider as well. This is, of course, it's mentioned here in note 2. A toroid basically would involve a current flux density that encircles the donut And if you were to take a trace on the XY plane, it would indicate that the current flux density J is either in the Z hat or minus Z hat direction, and that the field is in the theta hat direction. In this case, the left-hand side of Stokes' theorem is just 2 pi r, f of r being the radius of any circle parallel to the xy plane, centered on the axis of symmetry of the donut. In the solenoidal case, the current flux density in the theta hat direction, in which case we have two values to circulation contributions. One that's down the middle of, or like along the axis of symmetry. That'll have a contribution which is some constant times z, and outside the solenoid, the contribution will be 0. Z being the length of the contour segment. And finally, for the cylindrical case, it was 2 pi r f of r being the constant that we're trying to compute. It was only a function of the radius. R was the radius of any circle centered on the axis symmetry of the cylinder. So this was basically the radius of the contour segment. Let me then make some concluding remarks, given that this is the end of the course. I'll acknowledge the fact that this course has been intense, but you have a wealth of material to fall back on in future years if you want to dig more deeply into the subject. Look at the appendices and the reading assignments. Lots of information there. You'll find it very difficult to find that in other textbooks, and so you may find this very useful. Second is the course was difficult, but we needed to get you prepared for the course on electromagnetics, which is EC221S next term, which assumes that you have mastered vector calculus and in particular know how to apply the divergence theorem and Stokes' theorem. All right, and then the thing which is probably more important at this point is the specifics of the final exam, which will be posted as a OneNote entitled Exam. You will be told the content of each exam question and the marks assigned to each question. There are 6 questions. The exam posting will be uploaded after the last official day of classes, but no later than the weekend before your exam. We will be monitoring Piazza frequently in case you have any additional questions. And also for my own benefit, if you have any comments about the course and how to improve it, you can send me a personal email after your exams are over. Don't bother now, do it when you have some free time. I make changes to course every year based on the guidance I receive from students, particularly if it's constructive advice. This is the very first year that I have a complete set of notes and videos, and also the very first time we have test run the inverted classroom model. I would not be able to show you visuals and interactive figures in a traditional classroom setting. So I think there's a greater degree of richness in basically doing it this way around. The only thing is you have to be prepared in knowing exactly the questions that you need to ask me during the Q&A sessions. And finally, I wish you good luck on the exams and good luck and good health in the new year. Thanks very much. That's the end of the course.